Chapter 6, Lesson 2. We are studying Newton's second law. The lesson objectives for today's lesson are 1. State Newton's second law. Number 2. Explain why objects fall at the same rate. A great mystery. Discuss, number 3, how air resistance affects things. These are our key areas of study for this lesson. Let's focus and learn about Newton's second law. Here we have a shot putter, and you can see he's putting in great effort to move this very heavy piece of steel. The steel's got mass, and we've learned that mass corresponds to inertia, and that inertia is a resistance to a change in your motion. He's applying a force to this mass, and when you apply a force to a mass, you can accelerate it. And that's what he's trying to do. And all three of these things, force, mass, and acceleration, are related by what we're going to call Newton's second law. Forces cause acceleration. That's really what it comes down to. That's what this law is telling us. At least that's the first part of what it's telling us. We'll break it down here. When you have a shot put and you put a force on it, the acceleration of that shot put will relate to the size of the force you put on it. The larger the force you apply to it, the larger the acceleration. We say that acceleration is directly proportional to the force. So in other words, as the force goes up, the acceleration goes up. They go up and down together. So when he puts a force on that shot put, he is accelerating it. And the key to the shot put really is to get that shot to be accelerated to as high a speed as possible before you release it. How you doing there, big fella? Okay, well, we can't rush this. Let's get to the second part, though. Newton's second law. Mass. Mass relates to inertia, we said, and it resists acceleration. If we rearrange Newton's second law and write it as seen here, we see that force is divided by mass, and that would give us acceleration. But as you can see also, mass is indirectly proportional. Oh, that's easier said. That's not so easy to say, is it? Indirectly proportional to acceleration. So in other words, as mass goes up, acceleration actually would go down. Imagine a 10 Newton force on a 10 kilogram object. Force, 10, divided by mass, 10, gives you an acceleration of 1. If we increase the mass to 100 kilograms, but keep the force the same, we can see that 10 divided by 100 would equal 1/10. So by increasing the mass, we actually decrease the acceleration. That's an indirect proportionality. That's what we call that. Let's try to keep our units straight in all of this. You might want to jot this down. As you solve these problems, you need to include units and keep track of the units. Mass is in grams or kilograms. Acceleration is in meters per second squared. Kind of of a weird unit, but it's meters per second each second, and we just write it as meters per second squared. Force is in a unit of newtons. So let's keep those straight, and let's proceed onwards. I'd like to talk next about falling objects and return to that. We've been studying that in chapters 4 and chapters 5. The number that we came up with is 10 meters per second each second, or 10 meters per second squared. That is the rate at which objects fall. After a second, an object will be going at a rate of 10 meters per second. But after another second of falling, the object will have sped up to 20 meters per second. Another second goes by and it's sped up to 30 meters per second. Always up by 10 meters per second each second. But how can this be? Galileo performed this experiment purportedly on the Tower of Pisa, the Leaning Tower of Pisa, as pictured here. But how can that be? It's a mystery that the two objects should fall at the same rate. Most people think to ask the first question: which rock has the larger force? And of course, the larger rock has the larger force. That should be no surprise. If you ever try to lift up a big rock off the ground, it's harder to do. It's harder to lift than picking up some small pebble. So the forces on them are not equal. The force on the large rock is actually quite a bit greater than the small one. So why doesn't it accelerate at a faster rate? Well, the thing that sometimes people neglect to ask is this question: which rock has the greatest inertia? You see, the larger rock has a greater force acting on it. Gravity pulls on it with a stronger force. But it also has a lot more mass, and therefore a lot more inertia, and so will resist a change in its state. You can think of it this way: a large force divided by a large mass could give the same answer as a small force divided by a small mass, and in fact they do. Both give the same ratio or answer to be g. Little g we've been calling the acceleration due to gravity, and we has a value of 10 meters per second squared. Air resistance can mess with things, and so this is oftentimes what people confuse, is they see things that fall that are light and they don't seem to be going as fast, and then in that case air resistance may be at play here. For instance, a feather and a coin, they would actually fall with equal accelerations in a vacuum. In other words, without any air. But they are not going to fall equally in the presence of air. When falling in air, the coin falls quickly while the feather flutters to the ground, and the force due to air resistance diminishes or reduces the net force acting on the falling objects. So an object that has a lot of surface area and not a lot of weight can be greatly affected by air resistance. You've undoubtedly tried this, even though it's not very safe. Stick your hand out the window of a moving car. I can hear all of your mothers at this time saying, "Get that hand in the car!" But at any rate, here we have a situation which should resonate with you. The car traveling down the road slowly has very little, if any, effect on your hand. It's not until you speed up that the force becomes significant. So the faster you go, the more resistance, the more air resistance there is. So it's a factor of speed, air resistance is. And in fact, you can reach a terminal speed, we say, when you go so fast that the air resistance actually is just as large as your weight, and the two forces cancel, creating dynamic equilibrium. In fact, the terminal speed for skydivers is somewhere in the neighborhood of 150 to 200 kilometers an hour, depending on the weight and the orientation. So if they're falling with their legs kind of spread eagle, or if they're falling vertically, that would depend. That would make a difference as to how much surface area is exposed. A heavier person will attain a greater terminal speed than a lighter person because the force of gravity is stronger. And as I said, body orientation also makes a difference. Here's a question that I'm going to leave you with. Which experiences a greater air resistance force? A falling piece of paper or a falling elephant? Think on that and answer the quiz questions that follow. Thank you.